My name is Victoria Contreras, and this is Physics Lab 7, Lab M. So this lab, we're looking at a model that is observing a star moving in a curving motion. And observing the force, or what is causing this motion. So one of the questions we have is, how do we quantify this force? And what do we notice about the different components, the parallel and the perpendicular? So as we're looking throughout this, before we look at the actual model, take note that our net force is going to be the red arrow. Our perpendicular net force is going to be the blue arrow, and the parallel net force is going to be the black arrow. Okay, so here's the code. As you can see, this is where the mass is, and then just different things. Here's the delta time, and then we go down, and you can see that we are calculating the velocity and updating the position as we go along. Right here is the chunk of our data where we're calculating the dp over dt, or the change in momentum over change in time. And we say right here how the change in momentum over change in time is the net force, which is Newton's second law of motion. And then this is where we're just we're putting each arrow to each of the forces. So like I said earlier, we're going to have the red arrow equal the net force, and then the others. So let's go ahead and go and run this, and then I'll explain more. Okay, as you can see, you have the blue and the red arrows that moved in the same direction, which is going to be in the middle. This is because, as you can see, it's moving in a circular motion. The magnitude of the motion isn't increasing, but our net force is still going in a circular motion, which means there has to be a force in the middle. This is where our blue arrow comes in. That's going to be our perpendicular force, which is the direction of our momentum, which is changing, or which rather is being pulled towards the middle due to the black hole that we know is in the middle. Let me run it again, and you can take a look at the black arrow. The black arrow is going to be our parallel force, and you can notice it goes in the motion of our star and then switches as the star increases speed. So that is the actual module data, but what does it all mean? As I was saying earlier, we're looking at our parallel net force, our perpendicular net force, and just our net force in general. One of the things you'll notice is that dp over dt, as I said earlier, is your Newton's second law of motion, which lets us know that net force and dp over dt are equal to each other. The difference between these, actually, which applies both to the parallel and perpendicular aspects of these, are that for net force, it is the cause of our motion. It's something that we can't technically quantify due to all the different forces and variables in the universe. However, dp over dt is a position, is our speed, which is quantifiable. However, due to this law, we do know that these are equivalent to each other. So it's pretty cool. Without this principle, we would have no idea how to calculate a net force. Now we have, in this particular problem, the force that we are able to calculate, the net force. We are out in space, so we have the gravitational force between our black hole and our star. In order to calculate the mass of this, we just did some algebra and to calculate for one of the masses, and this is what we got: F net times the distance squared divided by the g constant divided by, or times the second mass, which gave us the mass of our black hole. But what if we were given a different black hole? Could we tell that this was different if the star stayed in the exact same motion? I said no, because if you have the momentum equals the mass times velocity, which equals the net force times time. So if our direction doesn't change, if our magnitude does not change, that means it is impossible for our mass to be different, because our mass equals our net force. Therefore, it would be the exact same mass. Yeah, so there you go.